Welcome. Today we will be talking about subgroups. Um, let's let G be a group and H be a subset of G. If H itself is a group under the operation induced by G, then we say that H is a subgroup of G, and we use the notation H less than or equal to G to denote that H is a subgroup of G. So if a subset H of the group G is itself a group under the operation of G, then we say that H is a subgroup of G. So observe that for a subset H to be a subgroup, it must satisfy, first of all, the closure property. That is, whenever xy belongs to H, x times y must also belong to H. And then H must satisfy all three properties of a group, and which were associativity, existence of identity, and existence of inverse of each element. And the associative property will automatically hold for elements of any subset H of a group G. So when we try to show that a subset is a subgroup, we can skip the proof of the associative property, because it holds automatically in any subset of a group G. We say that H is a proper subgroup of the group G if H is a subgroup of G and H is not equal to G. And we indicate this by writing H less than G. So here we are using the strict inequality to denote that H is a proper subgroup of G. The subgroups G and the subgroup G is called a trivial subgroup of G, and the subgroup containing only the identity element is also called a trivial subgroup of G. A subgroup that is not equal to the group with the identity, the subgroup with the identity only, or G itself, then it is called a non-trivial subgroup of G. So if I have a subgroup that is not equal to the entire group, and it is not equal to the subgroup containing the identity only, then it is called a non-trivial subgroup of G. NZ is a subgroup of Z under addition. So recall the Z is the set of integers, and NZ is the set of all multiples of n. So if I take n to be 2, then we are saying that 2Z is a subgroup of Z. Now 2Z is the set of all multiples of 2, which is basically the set of all even integers. So the set of all even integers is a subgroup of the set of the integers under addition. Recall that SL2 of R is the collection of 2 by 2 matrices with the real entries having determinant equal to 1. And GL2 of R is the collection of all 2 by 2 matrices with the non-zero determinant. So SL2 of R is a subgroup of GL2 of R. Recall that the set of if a matrix has non-zero, a matrix has a non-zero determinant if and only if it is invertible. So GL2 of R is also is also the collection of all invertible 2 by 2 matrices over the real numbers. Z is a subgroup of Q, which is the set of rational numbers. It's a subgroup of the set of real numbers, and that's the subgroup of the complex numbers. And so under addition, so this is under addition, Z is a subgroup of Q, Q is a subgroup of R, and R is a subgroup of C. And we can also say Z is a subgroup of C, and so on. Now recall that when I put star on one of these sets here, that's the set of all non-zero elements of that set. So the Q star is the set of all non-zero rational numbers, R star is the set of all non-zero real numbers, C star is the set of all non-zero complex numbers. And under multiplication, Q star is a subgroup of R star, which is a subgroup of C star. Again, notice that Q star is also a subgroup of C star. Okay, so here's an example. Let's say that G is an abelian group where the identity of this group is denoted by E, and let H be the subset of G, where where X belongs to H if the square of X is the identity. So H is a subset of G, where X belongs to H if the square of X is the identity. We want to show that H is a subgroup of G. Okay, so to show it's a subgroup of G, we have to show that H is itself a group under the operation of G. Here we are going to assume, again, we are using multiplicative notation for the group operation. So unless otherwise specified, we always assume a multiplicative notation for the group operation. Now, so to show that H is a subgroup, then I have to show that H is closed under the operation of G. So to show that, let's take xy in G, and by definition of H, we see that x squared has to be the identity, and y squared is also equal to the identity. This is because y belongs to H, and by definition of H, any element of H squared is the identity. Since G is an abelian group, we can say that the square of xy is the same as x squared times y squared, and because x squared y squared both of them are equal to the identity, we see that x squared times y squared is also equal to identity. So therefore xy squared is equal to the identity. So since the square of xy is the identity, by definition of H, xy belongs to H. So then we see that whenever xy belongs to H, x times y also belongs to H. And that shows that H is closed under the operation of the group G. The associativity clearly holds for elements of H, since H is a subset of G, where associativity holds true. So again, I mentioned it before that the associative property will automatically hold in any subset of the group, and so we don't have to prove the associative property to show that something is a subgroup. Okay, so the next thing I need to show is that the identity element, identity belongs to, so recall that the three properties of a group, right? The three properties are associativity property, the existence of identity, and the existence of the inverse of each element. So now we show that the identity belongs to H. So how do I show the identity belongs to H? Well, the identity belongs to H because the square of the identity is the identity, and by definition of H again, H contains the identity. So that's a easy one to see. Next, we want to show that every element of H, the inverse of every element of H is in H. So let's say that X is in H. Then if I take the square of X inverse, then that's the same as x to the negative 2, which in turn is the same as x to the 2 to the power negative 1. And because x is in H, we know that x squared is the identity. So the x squared here is the identity, but the inverse of the identity is also the identity. So we see that this quantity is equal to the identity, and as a result, we see that the square of the x inverse is the identity, and therefore x inverse belongs to H. So thus the inverse of any element x of H exists within H. We conclude then that H is a subgroup of G. So again, we showed that H is closed under the operation, that is, H satisfies the closure property. We showed that the identity is in H. We showed that the inverse of each element of H is in H. And we also saw that the associativity holds in H. So as a result, H is a subgroup of G. Okay, so let's now take H to be the set of all non-zero real numbers x such that x is either 1 or x is irrational. So the set H is basically the set of all irrational numbers, irrational real numbers, and H also contains the number 1. Now, is H a subgroup of R star under multiplication? So recall that R star is a group under multiplication because the identity would be 1, and every non-zero real number has a multiplicative inverse. Multiplication of real numbers is associative. So all the properties of a group holds for R star under multiplication. Okay, so is H a subgroup of R star? Well, it turns out that it's not. And the reason is H is not closed under multiplication. And you can see why that, root 2 is an irrational number. So root 2 belongs to H, but root 2 times root 2 is 2, which doesn't belong to H. So you see that H is not closed under multiplication, and therefore H is not a subgroup. One last example in this video. So here I take K to be the set of all non-zero real numbers which are larger than or equal to 1. So these are again the collection of all real numbers greater than or equal to 1. So is that a subgroup of R star under multiplication? Well, this time this K is in fact closed under multiplication. Why? Because if I multiply two numbers bigger than 1, then I get a number bigger than 1. That is, the product of two numbers larger than 1 is also larger than 1. So K is closed under multiplication. However, it's not closed under taking inverse. So that is, notice that the number 3 in K has an inverse 1/3, but that does not belong to K. So we have an element of K that doesn't have an inverse within K. So then we can say that K is not a subgroup of R star. Okay, so this is it for this video, and I will see you in the next video where we look at some subgroup tests.